As you rest peacefully tonight after another day, perhaps you witnessed one of nature's most spectacular displays. A sunset painting the western sky in shades of orange, pink, red and purple that seem almost too vivid to be real. This daily masterpiece occurs not through pigments like a painting, but through pure physics. Sunlight interacting with Earth's atmosphere in ways that separate white light into its component colors, creating the warm hues that have inspired artists, poets, and viewers throughout human history, with their ephemeral beauty that appears each evening only to fade into darkness. Tonight, as you drift towards sleep, you'll discover why sunset skies are colorful while midday skies are blue, how the atmosphere acts like a giant prism sorting light by wavelength, why sunsets turn redder as the sun approaches the horizon, what role air molecules and particles play in creating color, how pollution and dust affect sunset appearance, and why no two sunsets look exactly the same despite following the same physical principles, revealing that the beauty above you each evening emerges from elegant interactions between light and matter that physics can explain completely. Sunlight appears white because it contains all colors of the visible spectrum: red, orange, yellow, green, blue, indigo, and violet, mixed together in roughly equal proportions. This white light originates from the sun's surface, travels 93 million miles through the vacuum of space where it doesn't interact with anything, then encounters Earth's atmosphere where the real show begins. The atmosphere, despite appearing transparent, is filled with gas molecules and tiny particles that scatter light in wavelength-dependent ways, separating white light into colors and sending different wavelengths in different directions. The key to understanding colorful skies is Rayleigh scattering, named after Lord Rayleigh, who explained it mathematically in the 1870s. This type of scattering occurs when light encounters particles much smaller than its wavelength, primarily the nitrogen and oxygen molecules that make up 99% of Earth's atmosphere. These molecules are only about 1/billionth of a meter across, far smaller than visible light wavelengths, which range from about 400 nanometers violet to 700 nanometers red. Rayleigh scattering has a crucial wavelength dependence. Shorter wavelengths, blue and violet, scatter much more strongly than longer wavelengths, arc in red and orange. Specifically, scattering intensity is inversely proportional to wavelength to the fourth power, meaning blue light, wavelength approximately 450 nanometers, scatters about 10 times more than red light, wavelength approximately 650 nanometers. This dramatic difference in scattering creates both the blue daytime sky and the red evening sunset through the same underlying physics applied to different viewing geometries. During midday, when the sun is high overhead, sunlight travels relatively straight down through the atmosphere, perhaps 60 miles of air total. Blue light scatters strongly even in this relatively short path, bouncing off air molecules in all directions and filling the sky with blue light that reaches your eyes from every direction. The red and orange light scatters weakly and mostly continues straight through to Earth's surface, which is why the sun itself appears yellow or white at midday. It's sending mostly red, orange, yellow, and green light directly to you while the blue has scattered away. At sunset, the geometry changes dramatically. The sun sits on the horizon, so its light must travel through much more atmosphere to reach you. not straight down but at a shallow angle through perhaps 300 to 400 miles of atmosphere, 5 to 6 times farther than at noon. This extended path length gives scattering more opportunity to act, removing progressively more of the shorter wavelengths from the direct sunlight, leaving primarily the reds and oranges that scatter weakly and can survive the long journey through thick atmosphere. Think of the atmosphere as a filter that preferentially removes blue light. With a thin filter, short path at noon, some blue gets through and the sun looks yellowish-white. With a thick filter, long path at sunset, almost all blue is removed and only red and orange remain in the direct sunlight, making the sun appear deep red or orange. Meanwhile, the blue light that was scattered away earlier in the atmosphere creates the beautiful gradients you see. Red near the horizon where you're looking through the most atmosphere, transitioning to orange, yellow, and eventually blue higher up where sunlight passes through less air before scattering toward your eyes. The timing of sunset creates urgency in the color display. The most vivid colors appear when the sun is just at or slightly below the horizon, then fade rapidly as the sun sinks lower and its light no longer illuminates the atmosphere above you. The progression from bright daylight to colorful twilight to darkness typically takes about 30 minutes in temperate latitudes, though this varies with season, latitude, and atmospheric conditions, creating a natural time limit that makes each sunset a fleeting performance never to be repeated exactly. As you prepare to explore the physics of sunset colors tonight, rest in appreciation that this daily spectacle requires no effort on your part. The atmosphere automatically creates beauty through simple interactions between light and air, demonstrating that some of nature's most impressive displays emerge from basic physical principles operating on cosmic scales, where the sun's white light and Earth's thin atmosphere collaborate to paint the evening sky in warm colors that signal day's end and invite peaceful reflection before darkness falls. Rayleigh's gift: how small particles scatter light. Descend now into the molecular scale where Rayleigh scattering occurs, discovering how air molecules just billionths of a meter across interact with light waves thousands of times larger. Why this size mismatch creates wavelength-dependent scattering that sends blue light in all directions, while allowing red light to pass through, and how this simple physical process creates the foundation for all atmospheric color, from the blue of midday skies to the red of evening horizons. Air molecules, primarily nitrogen, N2, and oxygen, O2, are extraordinarily small, roughly 1 nanometer in diameter. Light waves passing through air have wavelengths of 400 to 700 nanometers, making them hundreds of times larger than the molecules they encounter. This size relationship is crucial. When light encounters objects much smaller than its wavelength, it undergoes Rayleigh scattering, which has very different properties from the scattering that occurs with larger particles. When an electromagnetic wave, light, passes near a molecule, the oscillating electric field of the light wave causes the molecule's electrons to oscillate at the same frequency. These oscillating electrons act like tiny antennas, radiating light in all directions. This re-radiation is what we call scattering. The molecule absorbs light traveling in one direction and emits it in many directions, effectively removing it from the original beam and sending it elsewhere. The intensity of this scattering depends strongly on wavelength, because shorter wavelength light oscillates faster, causing electrons in molecules to oscillate more vigorously, which produces stronger radiation. The mathematical relationship is that scattering intensity is proportional to 1 over wavelength to the 4th power. This means if you halve the wavelength, you increase scattering intensity by a factor of 16. 2 to the power of 4 equals 16. This dramatic wavelength dependence creates the color effects we observe. Blue light with wavelength around 450 nanometers scatters much more than red light with wavelength around 650 nanometers. The ratio is 650 over 450. To the power of 4 is approximately 4.5, meaning blue light scatters about 4 to 5 times more intensely than red light. Violet light with even shorter wavelength around 400 nanometers scatters even more strongly than blue. This raises an interesting question. If violet scatters most, why is the sky blue rather than violet? The answer involves both physics and biology. The sun emits less violet light than blue light to begin with. Its peak emission is in the green-yellow range, with decreasing intensity toward violet. Additionally, human eyes are less sensitive to violet than to blue. Our retinas have fewer receptors that respond to the shortest visible wavelengths. The combination means that, despite violet's stronger scattering, we perceive the sky as blue because blue light is both more abundant in sunlight and more visible to our eyes. The directionality of Rayleigh scattering also matters. Light scattered by molecules doesn't go equally in all directions. It's most likely to scatter perpendicular to the original direction, and less likely to scatter directly forward or backward. This means when you look at the sky 90 degrees from the sun, perpendicular to the sun's rays, you see the most intensely scattered light. This is why the sky appears deepest blue when you look perpendicular to the sun's direction rather than toward or away from it. Rayleigh scattering is elastic scattering. The scattered light has the same wavelength as the incident light, with no energy lost in the process. The molecule absorbs a photon traveling one direction and almost instantly emits an identical photon in a different direction. This preserves color purity and prevents the scattered light from appearing washed out or mixed. Blue light that scatters remains pure blue. Red light that scatters remains pure red. The number of scattering events matters for color separation. Each time sunlight encounters air molecules, a small fraction scatters. Through thin atmosphere, short path, sunlight experiences relatively few scattering events and mostly continues on its original path with only the most strongly scattering wavelengths, blue and violet, significantly depleted. Through thick atmosphere, long path at sunset, sunlight experiences many scattering events that progressively remove blue, then green, then yellow, leaving primarily orange and red in the direct beam. Temperature and pressure affect scattering by changing air density. At sea level, air contains about 2.5 times 10 to the power of 19 molecules per cubic centimeter. At high altitude, where density is lower, there are fewer molecules to scatter light, making the sky appear darker blue or even purple-black at extreme altitudes where the atmosphere becomes very thin. This is why astronauts see a black sky. From space, there's too little atmosphere above them to scatter significant light. The polarization of scattered light creates additional atmospheric optics effects. Light scattered by air molecules becomes partially polarized. The electric field oscillates preferentially in certain directions. This polarization is strongest when looking perpendicular to the sun and decreases when looking toward or away from the sun. Many animals, including some insects and birds, can detect this polarization pattern and use it for navigation, perceiving aspects of skylight that humans cannot directly see. As you rest peacefully tonight, imagine the countless trillions of air molecules above you, each one acting as a tiny antenna receiving sunlight and rebroadcasting it in all directions with wavelength-dependent efficiency, collectively creating through Rayleigh scattering the blue that dominates daytime skies and the reds that paint evening horizons, demonstrating the color in the sky emerges not from pigments or dyes, but from pure physics. Electromagnetic waves interacting with matter according to mathematical laws that determine exactly which wavelengths scatter and which pass through, creating beauty through physics as reliable and predictable as planetary orbits, yet as visually stunning as any human art. The long path home, atmospheric depth and color. Journey now through the geometry that creates sunset colors, discovering how the sun's position relative to the horizon determines the path length through atmosphere, why this path length dramatically affects which colors reach your eyes, how the curved Earth creates an even longer path than flat geometry suggests, and why sunset colors change rapidly as the sun sinks lower, creating the dynamic color display that makes each minute of sunset visibly different from the one before. When the sun is directly overhead at zenith, its light travels straight down through the atmosphere, the shortest possible path from space to Earth's surface. If the atmosphere extends about 60 miles, with most density in the lowest 10 miles, then zenith sunlight passes through approximately 1 air mass of atmosphere. This is the baseline for comparison. As the sun moves toward the horizon, the path through atmosphere increases because sunlight must travel at an ever more shallow angle. When the sun is 30 degrees above the horizon, the path length is about 2 air masses, twice as long as at zenith. At 10 degrees elevation, the path is about 6 air masses. Right at the horizon, 0 degrees, the path approaches 38 to 40 air masses, depending on atmospheric conditions and how you account for Earth's curvature and atmospheric refraction. This is why sunset colors change so dramatically. A small change in sun elevation near the horizon produces a large change in atmospheric path length. When the sun drops from 5 degrees above horizon to the horizon itself, the path length nearly doubles, providing much more opportunity for scattering to remove blue and green light from the direct beam. This rapid change in path length explains why sunset colors evolve quickly, with visible changes occurring within minutes. Earth's curvature increases path length beyond what flat Earth geometry predicts. As sunlight grazes the horizon, it doesn't travel in a straight line through uniform atmosphere, but curves through layers of decreasing density, following a path that's longer than a straight line would be. Additionally, atmospheric refraction, bending of light by density gradients, curves the light path further, allowing you to see the sun even when it's geometrically below the horizon. This refraction adds to the effective path length and contributes to the deep red color of the sun just before it completely sets. The atmosphere's vertical structure affects colors because density decreases with altitude. Most air molecules concentrate in the lower atmosphere. Half of all atmospheric mass lies below about 18,000 feet, and 99% lies below 20 miles. At sunset, when sunlight grazes horizontally through atmosphere, it spends more time in these dense lower layers where scattering is strongest. This bottom-heavy distribution of scattering enhances the removal of short wavelengths from horizontal light paths. The progression of sunset colors follows a predictable sequence as path length increases. When the sun is still well above the horizon, it appears yellow-white with a blue sky. As it descends to 10 to 20 degrees elevation, the sun becomes distinctly yellow and the sky around it warms to yellow-orange. At 5 to 10 degrees, the sun turns orange and the horizon glows with orange and yellow. Right at the horizon, the sun appears deep red or orange-red, and the sky shows bands of color. Red nearest the horizon, transitioning through orange and yellow to blue overhead. After sunset, when the sun has dropped below your horizon but still illuminates atmosphere above you, the colors can become even more spectacular. The underside of clouds may glow brilliant orange or pink as they catch sunlight that's traveled through enormous atmospheric path lengths. The sky shows a gradient from dark blue overhead, no longer receiving direct sunlight, through purple, pink, orange, and yellow near the western horizon, still illuminated by the setting sun. This twilight phase creates some of the most beautiful colors because you're viewing scattered light from multiple atmospheric layers, illuminated at different angles. The belt of Venus, a pinkish band that appears opposite the sunset just above the horizon in the eastern sky, results from sunlight scattered in the atmosphere and then passing through more atmosphere before reaching your eyes. The pink color comes from red light scattered at high altitude, passing back through the lower atmosphere where blue light is scattered away, leaving predominantly pink. Below this belt appears the Earth's shadow, a blue-grey band where the sun's light is blocked by Earth itself, creating a striking color boundary. Atmospheric thickness varies with latitude, season, and weather patterns, affecting sunset colors. Tropical regions have thicker, more humid atmospheres that create more scattering. Polar regions have thinner, drier atmospheres that produce less intense scattering. Seasonal changes in atmospheric thickness, humidity, and aerosol content create variability in sunset appearance throughout the year. This is why sunset colors at a given location aren't identical from day to day. Atmospheric conditions vary, altering the exact amount and type of scattering that occurs. The angle at which the sun sets also affects color duration and intensity. Near the equator, the sun sets almost vertically, dropping quickly below the horizon. Sunset colors evolve rapidly but don't last long. At higher latitudes, especially in summer, the sun sets at a shallow angle, taking longer to sink below the horizon. Sunset colors evolve more slowly and persist longer, sometimes creating extended twilights that last for hours in polar regions during summer months. As you drift toward sleep tonight, imagine the geometry of sunset occurring somewhere on Earth right now. Sunlight streaming horizontally through hundreds of miles of atmosphere, blue light scattering away early in the journey, green and yellow being removed progressively, until only the reds and oranges that scatter weakly remain in the direct beam. painting the sun deep crimson and illuminating the western sky in warm hues that signal day's end, all because of simple geometry combining with wavelength-dependent scattering to create the color progression that marks the daily transition from light to darkness. Beyond blue, additional colors in the sunset palette. Discover now the additional factors that contribute to sunset colors beyond simple Rayleigh scattering. How aerosols, dust and pollution add reds and purples. Why clouds glow brilliant orange and pink. What volcanic eruptions do to global sunsets. How water vapor affects color intensity. And why some sunsets appear more spectacular than others depending on atmospheric conditions that vary from day to day and place to place. Mie scattering, named after Gustav Mie, who solved the equations for light scattering by particles comparable to or larger than light wavelengths, contributes to sunset colors when the atmosphere contains dust, pollen, smoke, or pollution particles. Unlike Rayleigh scattering, which strongly favors short wavelengths, Mie scattering is less wavelength dependent, scattering all visible colors more equally. This has two effects. It creates a whitish haze in the daytime sky, washing out the pure blue, and it enhances red colors at sunset by scattering red light that Rayleigh scattering would allow to pass through. Dust and aerosols in the lower atmosphere are particularly important for spectacular sunsets. A clean atmosphere produces pleasant but relatively pale sunsets, the orange and yellow from Rayleigh scattering alone. Adding dust creates more intense reds and can produce purple and magenta hues through a combination of Mie scattering of red light and Rayleigh scattering of blue light. Scattering of blue light from different atmospheric layers. The most vivid sunsets typically occur when the atmosphere contains moderate amounts of particles. Too clean and colors are pale, too polluted and the sky becomes murky grey. Volcanic eruptions inject enormous quantities of particles into the stratosphere, the atmospheric layer 6 to 30 miles high, where they can remain for months or years, creating spectacular sunsets worldwide. The 1991 eruption of Mount Pinatubo in the Philippines injected enough sulfate aerosols into the stratosphere to create intensely colorful sunsets globally for over 2 years. These particles enhanced Mie scattering in the stratosphere, producing vivid reds, oranges, and even purples in sunset skies that were photographed and remarked upon around the world. The layered structure of colored bands you see at sunset results from light passing through atmosphere at different heights, experiencing different amounts of scattering. Near the horizon, light passes through the most atmosphere and appears deep red. Slightly higher, light passes through less atmosphere and appears orange. Higher still, yellow appears, then blue overhead. These color bands are not discrete layers, but gradients created by the continuous variation in atmospheric path length with viewing angle. Clouds add dramatically to sunset colors by acting as screens that display the colored light of sunset. The underside of clouds lit by sunset receives primary red and orange light, the colors that have survived the long atmospheric path. High clouds that catch sunlight when lower clouds and ground are in shadow can glow brilliant orange, pink, or even red, creating dramatic three-dimensional effects. The contrast between bright, warm-colored clouds and the darkening blue sky creates some of the most striking sunset scenes. The purple and magenta hues, sometimes seen in spectacular sunsets, result from the combination of scattered blue light from high altitude mixing with scattered red light from lower altitude. This requires specific conditions: a clean upper atmosphere to provide intense blue and sufficient aerosols in the lower atmosphere to scatter red light upward. When your eyes receive both wavelengths simultaneously from slightly different atmospheric regions, your brain interprets the mixture as purple or magenta, creating colors that don't have a single wavelength in the spectrum. Water vapor content affects sunset intensity through several mechanisms. High humidity can create haze that washes out colors through excessive scattering. Moderate humidity can enhance colors by providing additional particles, tiny water droplets for scattering. Very low humidity, desert or high altitude conditions produces extremely clear air that allows pure Rayleigh scattering, creating intense blues during day and pure saturated oranges and reds at sunset without the murkiness that humidity can introduce. Industrial pollution can enhance or degrade sunset colors depending on particle type and concentration. Sulfate aerosols from burning fossil fuels can intensify reds similarly to volcanic aerosols. However, excessive pollution creates brown or grey haze that obscures rather than enhances sunset colors, making sunsets in heavily polluted areas less vivid than in moderately polluted or clean locations. This is one reason why desert locations often have spectacular sunsets. Clean, dry air allows pure colors without haze. Wildfire smoke can create extremely dramatic sunsets. The particles from burning forests and vegetation are effective at scattering, particularly of red light. During major wildfire events, smoke can transport hundreds of miles downwind, creating unusually intense red sunsets far from the fires themselves. The sun may appear blood red even at midday when smoke is particularly thick, demonstrating how aerosols can dramatically alter the appearance of sunlight reaching Earth's surface. The position of clouds relative to the sun creates varying effects. Clouds between you and the sun at sunset appear backlit, dark against the bright sky, though their edges may glow with transmitted orange light. Clouds beside or opposite the sun receive reflected/scattered sunset light, glowing with the warm colors characteristic of sunset. High clouds above the sun's position as it sets may continue glowing for 20 to 30 minutes after the sun drops below the horizon, catching sunlight at altitude while the surface is in shadow. Contrails from aircraft can enhance sunset displays by creating artificial clouds that catch and reflect sunset colors. These linear clouds, made of ice crystals formed from aircraft exhaust, can glow brilliantly orange or pink, creating dramatic streaks across the sky. While some view them as detracting from natural beauty, they do contribute to the optical display through the same physics that affects natural clouds. As you rest peacefully tonight, appreciate that sunset colors emerge from multiple interacting factors. Rayleigh scattering, providing the foundation of blue to red color separation. Scattering from particles, adding intensity and additional reds. Atmospheric layering creating color gradients. Clouds acting as screens, displaying the filtered light. And weather conditions determining humidity and aerosol content, all combining differently each evening to create the unique display that appeared today, ensuring that while sunsets follow consistent physical principles, no two are ever exactly identical in their particular combination of color, intensity, and cloud arrangement. Around the world. How location affects sunset. Journey now around the world to discover how sunset appearance varies with latitude, altitude, season, and local conditions. Why tropical sunsets differ from polar twilights. How elevation changes atmospheric thickness and color intensity. Why some locations reliably produce spectacular sunsets, while others rarely do. And what creates the variations in sunset timing, duration, and color palette across Earth's diverse environments and climates. Latitude dramatically affects sunset characteristics through two main mechanisms: the angle at which the sun sets and the seasonal variation in day length. Near the equator, the sun sets almost vertically, dropping straight down toward the horizon. This rapid descent means sunset colors evolve quickly, but don't last long. The sun typically sets in about 2 to 3 minutes, and twilight is brief. The vertical setting geometry also means less variation in atmospheric path length as the sun descends, producing less dramatic color evolution than higher latitudes experience. At higher latitudes, the sun sets at an increasingly shallow angle. At 60 degrees latitude, roughly Alaska or Norway, summer sunsets take 5 to 10 minutes for the sun to disappear below the horizon, and twilight can last for hours as the sun slowly circles just below the horizon. This extended sunset creates more gradual color changes and allows sunset hues to persist longer. In midwinter, at these latitudes, the sun barely rises above the horizon, creating all-day sunset-like lighting conditions with warm colors even at midday. Polar regions experience the most extreme sunset variations. During summer, the sun circles the horizon without setting, creating 24-hour daylight with continuous low-angle illumination that produces perpetual sunset-like warm lighting. During winter, the sun remains below the horizon, creating prolonged twilight conditions where the sky may show sunset colors at local noon, even though the sun never appears. These extreme conditions demonstrate how solar geometry creates fundamentally different lighting environments at different latitudes. Altitude affects sunset colors primarily by reducing the atmospheric thickness above you. At sea level, you have the full atmosphere above you to scatter light. At high altitude, on mountains or in aircraft, you have less atmosphere above, which changes the balance of scattering. The sky appears darker blue during day because less air above you scatters light into your eyes. At sunset, colors can be more intense because you're above some of the haze and humidity that can wash out colors at sea level. Desert locations typically produce spectacular sunsets because of their dry, clean air combined with occasional dust. The Sonoran Desert, the Sahara, the Australian outback, these regions experience clear, unpolluted air most of the time, allowing intense Rayleigh scattering colors. When dust is present from wind or storms, it enhances reds through scattering without the murkiness that humidity would introduce. The combination creates intense, saturated colors that desert locations are famous for. Coastal areas often show beautiful sunsets because of moisture and particles above the ocean. Sea salt aerosols from breaking waves, maritime moisture, and the contrast between water and sky create favorable conditions for colorful sunsets. However, extensive cloud cover common in some coastal climates can obscure sunsets, making clear evenings particularly valued when they occur. The reflection of sunset colors in water, whether ocean, lake or river, doubles the visual impact by creating a mirror image of the colorful sky. Mountain ranges create unique sunset effects through both altitude and topography. Viewing sunset from a high peak places you above much atmosphere, creating intense colors. Mountain ranges also cast long shadows during sunset, creating dramatic contrasts between illuminated and shadowed areas. The alpenglow, a pink or red glow on mountain peaks after sunset, occurs when these high elevations catch the last direct sunlight, while valleys below are already in shadow, creating a spectacular effect visible from lower elevations. Tropical regions experience less variation in sunset timing throughout the year because of their proximity to the equator, where day length varies minimally with season. Day length at the equator remains close to 12 hours year-round, with sunrise around 6 a.m. and sunset around 6 p.m., varying by only minutes seasonally. This consistency means sunset occurs at predictable times, useful for activities and rituals tied to sunset timing. In contrast, high latitudes experience dramatic seasonal variation. Summer sunset might occur at 10 p.m., while winter sunset happens at 4 p.m. The timing of seasonal changes affects sunset quality in different climates. In temperate regions, fall and spring often produce the most spectacular sunsets because of atmospheric conditions. Transitional weather patterns, varying moisture levels, and moderate temperatures that create favorable aerosol distributions. Summer heat can create haze that washes out colors, while winter cold can produce extremely clear air but with less moisture to scatter light. The intermediate seasons balance these factors optimally. Urban versus rural locations show different sunset characteristics, primarily through pollution and light pollution. Cities often have more aerosols from traffic and industry, which can either enhance or degrade sunsets depending on particle type and concentration. Light pollution from cities makes it harder to appreciate the full range of twilight colors, particularly the subtle blues and purples that appear in a dark sky after sunset. Rural locations away from artificial light reveal the complete color progression as natural twilight deepens. Weather patterns influence sunset appearance dramatically. High-pressure systems typically bring clear, dry air that produces clean, intense colors. Low-pressure systems bring clouds that can either obscure sunset completely or create dramatic displays when clouds are positioned favorably. Frontal boundaries, where air masses meet, often produce spectacular sunsets because of the varied cloud types and aerosol distributions associated with weather transitions. Seasonal atmospheric events affect sunset colors predictably in some regions. The southwest United States experiences intense summer monsoon patterns that create dramatic cloud formations and dusty conditions, both enhancing sunset displays. Southeast Asia's monsoon seasons bring extensive cloud cover that can obscure sunsets for weeks, making clear sunset evenings particularly prized. These predictable patterns mean locals in different regions learn when their location typically produces the best sunsets. As you drift towards sleep tonight, imagine people around the world experiencing sunset at this very moment. Equatorial dwellers watching rapid vertical descents with brief but intense colors. Polar residents experiencing extended twilights lasting hours. Mountain climbers viewing from altitude with the world shadowed below. Desert wanderers seeing saturated reds in crystalline air. and coastal observers watching colours reflected in water, all witnessing the same physical phenomenon, sunlight through atmosphere, yet experiencing it in uniquely varied ways determined by geography, season, and local conditions that ensure sunset remains an infinitely variable show despite following universal physical laws. The beauty of physics. What sunsets teach us. Rest now in contemplation of what sunset science reveals about the nature of light, atmosphere, and perception. How understanding the physics enhances rather than diminishes appreciation for sunset beauty. Why the same principles that create evening colors also explain the blue of day and the white of clouds. What sunset observations taught scientists about atmospheric composition, and how this seemingly simple phenomenon connects to fundamental principles of optics, atmospheric science, and even the nature of perception itself. The wavelength dependence of Rayleigh scattering, the lambda to the power of -4 relationship that creates colored skies, is a fundamental consequence of how electromagnetic waves interact with matter much smaller than their wavelength. This same physics applies far beyond Earth's atmosphere. It explains why nebulae in space show colors based on what wavelengths scatter most from dust grains, why the atmospheres of other planets appear colored differently based on their atmospheric composition and density, and why light propagating through any medium with small particles experiences wavelength-dependent scattering. The study of sunset and sky colors historically contributed to atmospheric science. By analyzing how colors change with time and atmospheric conditions, scientists deduced information about atmospheric thickness, composition, and the distribution of particles at various altitudes. Before satellites and direct atmospheric measurements, careful observation of optical phenomena like sunsets, halos, and rainbows provided crucial data about the invisible atmosphere, demonstrating how visual beauty can be a source of scientific information. Sunset colors demonstrate that white light is composite rather than pure, a lesson that took centuries to fully understand. Newton's experiments with prisms showed that white light contains all colors, but everyday experience with sunlight appearing uniform and colorless obscured this fact. Sunsets provide a natural demonstration that white light really does contain distinct wavelengths that can be separated by differential scattering, making the physics visible without requiring laboratory equipment. The comparison between Earth's sunset and those on other planets reveals how atmospheric composition affects colors. Mars has an extremely thin atmosphere, 1% of Earth's pressure, composed primarily of carbon dioxide, with significant dust. This creates opposite color effects from Earth. Blue sunsets and red daytime sky because the reddish dust particles scatter red light more than blue light. My scattering dominates over Rayleigh's scattering. Photos from Mars rovers show these alien sky colors, demonstrating that the same physics produces different results with different atmospheric conditions. Venus has a thick atmosphere, 90 times Earth's pressure, composed primarily of carbon dioxide with sulfuric acid clouds. The extreme atmospheric thickness and cloud cover means sunsets on Venus would appear very different from Earth. If you could see them through the clouds at all, the atmosphere would scatter light so efficiently that the sky might appear bright in all directions even at sunset, and colors would be heavily influenced by the yellowish tint from sulfur compounds and the extreme optical thickness of the atmosphere. Titan, Saturn's largest moon, has a thick nitrogen atmosphere with hydrocarbon haze. Sunsets on Titan would appear orange or reddish throughout the event because the haze particles scatter light differently than Earth's molecular atmosphere. The dimmer sunlight at Saturn's distance, about 1% of Earth's intensity, would also create fainter sunset colors. These alien sunsets demonstrate how atmospheric physics applies universally, but produces varied results depending on local conditions. The perception of sunset colors involves not just physics, but also biology and psychology. Human color vision evolved to distinguish fruits, judge ripeness, and read facial expressions in daylight conditions. Our eyes are most sensitive to green-yellow light, where sunlight peaks, less sensitive to red and violet extremes. This means we perceive the color palette of sunsets through a biological filter that emphasizes the wavelengths our evolution deemed most important, making sunset a perceptual interpretation of physical reality rather than an objective representation. Cultural responses to sunsets vary worldwide, but almost universally involve appreciation for their beauty. Sunsets mark transitions, day to night, work to rest, activity to contemplation. Many cultures have rituals, prayers, or traditions associated with sunset time. The reliability of sunset's daily occurrence, combined with its variability in appearance, creates a natural focal point for reflection and appreciation. That humans worldwide pause to watch sunsets suggests a deep aesthetic response to the physical display of scattering light. Photography and artistic representation of sunsets face interesting challenges because cameras don't perceive color the same way eyes do. Film and digital sensors have different spectral sensitivities than human vision, often capturing colors that look wrong compared to how the scene appeared in person. This demonstrates that color is not solely a physical property, but also involves the detector, whether human eye or camera sensor, and the processing system interpreting the signals, whether human brain or image processing software. The scientific understanding of sunsets enriches appreciation rather than diminishing it. Knowing that colors emerge from scattering doesn't make them less beautiful. It reveals the elegant physics underlying the beauty, showing that nature creates visual splendor through simple rules applied consistently. The fact that sunset colors follow mathematical laws makes them no less moving to witness, any more than understanding musical acoustics reduces the emotional impact of a symphony. The predictability of sunset timing and the unpredictability of sunset appearance create an interesting duality. You can calculate exactly when sunset will occur months in advance using astronomy and geometry, but you cannot predict exactly what colors will appear until you observe them, because they depend on atmospheric conditions, humidity, aerosols, clouds, that vary day to day and are difficult to forecast accurately. This combination of predictable timing and surprising appearance keeps sunsets interesting and worth watching repeatedly. Sweet dreams beneath the sky, where scattered light created today's blue ceiling and will create tomorrow evening's warm palette, where physics and beauty converge in the daily demonstration that science reveals rather than removes the magic from natural phenomena, and where each sunset serves as a reminder that you live in a universe governed by comprehensible laws that consistently create experiences worth pausing to appreciate, whether understood through physics equations or simply witnessed with eyes that evolved to see beauty in the wavelengths that survive. Atmospheric scattering when the sun approaches the horizon, and light must travel hundreds of miles through air before reaching you with its message that another day ends in a display of color that requires nothing but sunlight, atmosphere, and the principles of optics that have operated unchanged since Earth first developed its envelope of air billions of years ago. As consciousness fades into dreams, the sun continues setting somewhere on Earth's rotating surface, light streaming through ever thicker atmosphere, blue wavelengths scattering away to paint distant skies, red wavelengths surviving the long journey to create warm colors at the horizon, clouds catching and reflecting the filtered light, particles contributing their scattering to enhance the reds, and observers pausing to watch the daily display that emerges from simple physics applied to sunlight and atmosphere, creating through natural law the beauty that marks the transition from day to night, reminding everyone who watches that the universe operates by principles that consistently produce wonder, that understanding enhances rather than diminishes appreciation, and that each sunset, while following the same physics as every sunset before it, appears unique in its particular combination of atmospheric conditions, cloud formations, and viewing geometry, ensuring that this daily phenomenon remains forever fresh, forever worth watching, forever demonstrating that natural beauty emerges not despite physical law, but because of it, revealing a universe where mathematics describes not cold mechanism, but the elegant principles that paint the evening sky in colors that speak simultaneously to aesthetic sense and scientific understanding, bridging human appreciation and physical reality in the transitional moments when sunlight and atmosphere collaborate to transform day's white light into evening's warm palette before darkness falls and stars emerge in the deepening blue that follows sunset's brief but brilliant display.